It's the shortest discussion ever. Quadrilaterals have 4 sides. Why? It's the quad part of quadrilaterals, right? But then a lengthier discussion is, well, what kind of quadrilaterals are there? You have just the generic 4-sided figure. You can see under quadrilaterals, I get that. Doesn't really show you much of anything. You have the kite, right? Symmetrical figure generally, but if you think of 2 back-to-back triangles, that gets you into the way of thinking about a kite, right? So, and we'll talk about that as we go. Trapezoid, right? So 2 parallel sides, 2 non-parallel sides. Right. That's pretty straightforward relationship. I mean, it's a nice visual too. You know, you just kind of look at it and say, oh yeah, here's my 2 parallel sides here and here. And the other 2 definitely don't look parallel. Right. I mentioned this at one point in passing very briefly, but when we want to say, or we want to mark a diagram as having parallel sides, the way we do it is with little arrowheads. Right, so that notation there tells us that the 2 sides are considered to be parallel to one another. Right. So we haven't really used that notation very often. So it's kind of a quick conversation, but you know, it's worth noting here because when I get to an isosceles trapezoid, I see I have my 2 parallel sides and 2 non-parallel sides, absolutely. But what makes it an isosceles trapezoid is that it's a trapezoid with non-parallel sides that are congruent. Right? So they're congruent to one another. So geometrically, they're equivalent in length. Right? So, and again, we just use a little tick mark to indicate 2 sides are considered to be congruent to one another. Right? So an isosceles trapezoid is a trapezoid and then some, but then you kind of think about it as like, well, of course it is, because it's got trapezoid in the name and another word, right? What I like to think of in terms of an isosceles trapezoid is I kind of imagine an isosceles triangle, if you remember what those are. Those are triangles with 2 sides congruent. It's an isosceles triangle with the head chopped off. Right. So I cannot write, as we've noted throughout the semester. I'll say top chopped off. Another way sounds kind of morbid, even when talking about triangles, like that poor triangle. Never knew it hit him. I'm just going to make it look a little nicer as the story goes. That last little bit there didn't quite fit the way I wanted it to. And then oh, whoa, holy. Overdid it there. Okay, so yeah, again, we would just be getting rid of this piece. This is gone. All right, and kind of an interesting little side commentary here. It's not really anything overly complicated. It's just if you look at an isosceles triangle where you chop the top off, what you'll get is an isosceles trapezoid, but the part that you chopped off will actually still be an isosceles triangle, right? Which is what I was talking about with the Great Pyramid before, because if you think about it, anytime I chop part of the head off, and let me get that, put all the effort into putting these little markings in here, and now I got to take them all out. Anytime you chop part of a trapezoid off, so let's say I chop it off here. Now I have another trapezoid, which is parallel to the base trapezoid, right? So I get a second trapezoid. but an isosceles triangle right here. If I chop it again, I got a little tiny isosceles triangle, but now I have 3 isosceles trapezoids. I could keep going and going and going until I have this infinitesimal little distance. If it comes to a flat top, so let's say I stopped right here and just connected it, just like this. That whole thing is still an isosceles trapezoid. It isn't until I put the head on, that little triangular piece at the top, that it becomes an isosceles triangle. Right? So you can kind of look at triangles as being parts of quadrilaterals, but you could also look at quadrilaterals as being parts of triangles. All right. Well, now these little markings here are going to look ridiculous, so let me get rid of it. All right. So it's little things like that because you're repeating a pattern over and over again. Like what is it called? Sierpinski. I gotta look it up. It's the Sierpinski triangles. Sierpinski. I just gotta make sure I'm right before I bring it up on the screen because I'll find out that it's like something horrific. Sierpinski triangle. Oh yeah. Airdrop. 7. Bring it in. Okay. That was. So just looking at this, you see, I'll just tap on one of them. This one here. It's you start off with a triangle and you create a pattern out of it, but then that pattern repeats itself over and over again. All right. So it's anytime you're creating a pattern and then repeating that pattern over and over again, even if it gets smaller, it's it could be considered a tessellation, but it's also the beginnings of discussion of fractals. Right. So it's just a more infinitesimal discussion of a repeated pattern over and over again. Kind of like Doctor Strange did it pretty well. Like in different universes that are made up of repeating patterns over and over again. If you remember in the first Doctor Strange movie, if you've ever saw it, there was that one universe that just seemed to be made up of his hand, and then his hand splintered off, and like one finger became another hand, and then the pinky of that finger became another hand, and so on. It got smaller and smaller. It's just a repeated pattern, not overly complicated in terms of thought, but when you think about applications of it, it gets pretty crazy. So that was just a quick aside related to patterns and the useful. I don't want Siri. I mean, sorry, Siri. I don't have a problem with you. I just don't need you right now. Right? And by preparing my library for a faster experience. There we go. So that's the idea of an isosceles trapezoid. But if you wanted to, you could actually apply that approach with an ordinary trapezoid. Anytime you create parallel lines, it's gonna create more and more of those trapezoids that are smaller and smaller and smaller. All right. The parallelogram is a quadrilateral. I mean, they're all quadrilaterals, but opposite sides are parallel. Right. Opposite sides are parallel, and there's no other requirement in order to become a parallelogram, but there are other properties. Right. So, we'll get into that as we go forward, but just a quick example. If I draw the diagonals in a parallelogram, so if I draw a diagonal here, I create 2 congruent triangles. All right. This triangle here would be equivalent to that in terms of angles, lengths of sides, and area. Okay, so congruent as in geometrically the same. But Also, I could have drawn the diagonal this way. Those two triangles would be equivalent in length of side, area, and angular measure. All right. Now, if I draw both of those diagonals, they will cut each other in half. They'll bisect each other. All right. So these are going to bisect each other. These two line segments will be congruent. These two line segments will be congruent. Right. Now, the way it kind of, I mean, it definitely plays out. We can prove it, but maybe that's a conversation for later. If opposite sides are parallel to one another, they must also be the opposite sides. They must also be congruent to one another. Right. So that's something that we could prove later on, but that's another property of parallelograms. It's all in the table below, so I'll get into that in a minute. You get to two different pathways that emerge from the parallelogram. You get the rectangle, you get the rhombus. There should be a little arrow here, little breaking off point. All right. So a rhombus is a parallelogram with all sides congruent. So all sides have the same measure. I can draw a congruent from it. A rectangle is a parallelogram in which all the angles are congruent. Then you get to the square, which in terms of shapes, maybe you think about learning your shapes when you're much younger. You think, hey, you know what? I think I could draw a shape. It's pretty easy. I'm sorry, a square. It's pretty easy. But then I ask you to prove that something is a square. And you're like, oh, wait a minute. This actually seems like it's the most complicated one. Right? Because it's the end of a little diagram here, a little flow chart. Right? So the quadrilateral, just the general quadrilateral, is the most straightforward because it's all you got to do is demonstrate or show or prove that there are four sides to the figure. Okay, that's fine. To make something a trapezoid, you need to have two parallel sides. Okay, to make something a parallelogram, those other two sides also have to be parallel. To make that parallelogram into a rhombus, not only does it need to be a parallelogram, all the sides have to be congruent. Right? In order to make a parallelogram into a rectangle, it has to be a parallelogram where all the angles are congruent. Now, in order to make a square, it has to be a parallelogram with all sides and angles congruent. So all sides congruent and all angles congruent. So that's just the tip of the iceberg. Or the tip of the Great Pyramid of Giza. So a square could also be thought of as a rhombus in which all angles are congruent. Because if you think about it, a parallelogram with all sides congruent is a rhombus. Parallelogram with all angles congruent is a rectangle. If you want to put those two ideas together, we need, well, really three ideas. The first is the parallelogram. And by the way, this symbol here, just a slanted rectangle, it doesn't matter the quality of it. Anytime you draw a slanted rectangle, that's a parallelogram symbol. All right. So in order to make a square, I would want to show that we have a parallelogram and all sides congruent and all angles congruent. I'm going to use the angle symbol there. All right, but that's all. Like I said, it's only the tip of the iceberg, because that's what we said here. But I could also say it's a rhombus, or a rhombus and all angles are congruent. And one final or, I'm just going to kind of move this up here. A rectangle and all sides are congruent. Honestly, when you learn geometry back at a much younger age, it's probably the last one here that you think about. A rectangle with all sides congruent. It's like, okay, well, what's a rectangle? Okay, now imagine all the sides are congruent to one another. Oh, that's a square. All right, there you go. So, but that's the thing in terms of a proof. Look like a kind of a face there. I think it's squiggly. In terms of a proof, we need to be on guard for any of these possibilities, which is why I have this little table at the bottom here. Like just kind of going through all the different properties that a quadrilateral, I almost said parallelogram, quadrilateral could have, and that would be, like all sides congruent, opposite sides congruent, opposite sides parallel, things like that. So if you go through this, you see all sides congruent, that would be the rhombus and the square. Right? All sides, opposite sides are congruent. That's pretty much everything except for the first three that we talked about: the trapezoid, the isosceles trapezoid, and the kite. Right? Opposite sides parallel, same deal. Opposite angles congruent, same deal. All angles are right angles. It only happens in two instances. Right? Diagonals bisect each other. That's what I was talking about with the parallelogram. But if it happens for the parallelogram and a rectangle, and I kind of look at this sort of as a family tree, so you look at, and it's kind of weird to think about it, but like quadrilaterals are like this, the head of the family, and then it breaks up into different categories, so you got the kite. The kite doesn't have any descendants, okay? But the quadrilateral has a descendant, that is the trapezoid, okay? Which, when you start getting into family, like references of family trees and things like that, it's like, well, what kind of verbiage do you use? So it's like they got together and had a kid. It just never sounds fun and interesting that way. But yeah, it's kind of like if you took a trapezoid and improved upon it, maybe. Like, what are some things that could happen? Like you could have instead of those two other sides, the non-parallel sides just being non-parallel and left to their own devices, an improvement would be that they're parallel also to one another, making a parallelogram, or they're congruent to one another, making a trapezoid, isosceles trapezoid. And then an improvement on a parallelogram is you can take those slanted sides and straighten them out, making a rectangle, or you can shorten up those horizontal sides and make it a slanty square. Right, that would make the rhombus. Straighten that out, now you have a square. All right, so if you kind of follow the progression here, just like the most general to the most specific, then you get from quadrilaterals to squares specifically. But there's a lot going on here because, like diagonals congruent. Right, if you took a ruler and measured rectangles, diagonals, like drew them in there, and drew those rectangles, diagonals, and then measured them. Same thing with the square, you'd see that they're congruent, but you can probably visualize that. Like off the top, are you going to be thinking necessarily that an isosceles trapezoid has diagonals that are congruent? Maybe, maybe not. Right? That would require probably a little investigation. Diagonals are perpendicular. Right? unless you draw, a physical square that's damn near perfect, you're probably not going to be able to see that the diagonals are perpendicular to one another. But even still, it's also true of a rhombus and a kite. Like, whoa, okay, so what happened there? So you look at the kite. Now, the word is off center, but this is symmetrical. So if I draw this line segment here and this line segment here, well, the fact that I just drew a vertical line segment and a horizontal line segment should make it clear that they are going to be perpendicular to one another, right? Because vertical lines and horizontal lines are perpendicular. But if this was at an angle, maybe not the case, right? Or at least, I mean, it would definitely be perpendicular. It might not be obvious though, right? But then you get to the rhombus and you say, well, that's not going to be true for a rhombus. Now, I will preface this by saying it may not be true for this rhombus because I didn't do such a hot job of constructing this one, but these two line segments, okay, are actually perpendicular to one another. And that's also true for a square. Right. Now, in particular for a rhombus and a square, you got to consider a lot of different things going on here. First off, if they're parallelograms and parallelograms have diagonals that bisect each other, then these two line segments are congruent in length, and these two line segments are congruent in length. Same deal here. But in the case of the square, if those two line segments are congruent in length to begin with, the two diagonals, when you split them in half, then all four of these line segments are going to be congruent in length. Okay? And so what we just showed is that these four triangles, 1, 2, 3, and 4, are congruent by SAS. Right? We'd have a side, angle, and another side. All four of these triangles will be congruent to one another. So if I need to produce a square, all I'd have to do is create an isosceles triangle, right? Because it doesn't matter what the other side is. It would naturally work out. An isosceles triangle, I mean, all four of these sides are going to be congruent in length also, but to each other, not to the half diagonal values. So if I create one isosceles triangle and replicate it 3 more times, piece it together, I can get a square out. Right? So you think about production of materials, maybe you don't, in order to create a square, maybe you don't need to create a square. Maybe you just need to create triangles over and over again. It kind of makes me think of Comic-Con. It's an iffy comparison, but they were doing a Lego master build, and during this master build, they had these little stations there where all you had to do was take I think it was 20 pieces of Lego, put them together in some prescribed way. They gave you all the instructions, and just do that over and over again. It wasn't a free build. It wasn't do what you want. It was just make that same piece over and over again. So you're starting off these little pieces, putting it together to make one construction. And it was just some weird L shape, which the master builder then took and made the real build out of it. Right? So using those same pieces over and over again, same pattern over and over again, they did it with just straight rectangular solids. They were able to make, I believe that one was Batgirl. So it's all these different things, that can come from just repeated patterns over and over again, and you don't even realize it. Right? So all these things, they're pretty important properties, but you don't really recognize it just from one sheet of paper that's marked up. It's like, all right, yeah, I'm sure it's really incredibly important, but you don't realize it until you start diving into it. Right? Some some true false, well, not really true false, it's sometimes, always, never. Okay, so we'll just go with S for sometimes, A for always, N for never. A rectangle is a parallelogram. Right? So you got, it's the logic of it. Right? So a rectangle, you say a rectangle is, if I give you a rectangle and I call it a parallelogram, am I wrong? Well, a rectangle is a type of parallelogram, so I would be right to say that a rectangle is a parallelogram. So that would be always true. Right? A rhombus is a square. Well, a rhombus can be a square. A square is a type of rhombus, but there needs to be other information given. Like if I tell you that this figure is a rhombus, I could also be talking about a square if all four angles are congruent. So this is a sometimes. And the same would hold true for a parallelogram being a rhombus. A parallelogram would be a rhombus if all of the sides are congruent. So I'll actually make a note, always if all sides are congruent. But it's still a sometimes, right? And just going back to the previous one, it's always if all angles are congruent. A rhombus is a rectangle. You know, you just ask yourself again, is there a world in which I could call something a rhombus, but I really mean a rectangle, and I'm kind of right? A rectangle, the only thing that they have in common is that they're both types of parallelograms. Okay, so going back to what makes something a rhombus, all sides have to be congruent to one another. Opposite sides have to be parallel, but that makes it a parallelogram. All angles have to be congruent. So again, in order to be a rectangle. So if we're starting off with a parallelogram, we would have either the rhombus or the rectangle. But not both. Right? It can't be both at the same time. You know, there's no case where I'd say, oh, it's a rectangle, but under some circumstances, that rectangle could also be considered a rhombus and vice versa. So this is the never. Right? The only thing that they have in common is that they're parallelograms. Right? But you'd have to really kind of change the structure of things in order to make that rhombus into a rectangle. All right. A square is a rhombus, that's true, that's always. Right? If I say this is a rhombus, but you're looking at a square, I'm not wrong, I'm just not being as specific as I can be. A rectangle is a quadrilateral. Well, they're all quadrilaterals, so that's always. A square is a rectangle. A square, under all circumstances, is considered a rectangle. Again, it's the same idea as a square is a rhombus, right? So if I say square and you say rhombus, and you say rectangle, we're both right. Right? A rectangle is a square. It can be, but only if all four sides are congruent. So sometimes. Right. So the only weird one is the never. The one case where the rhombus is a rectangle. It seems like, well, if you can follow the path to get from one place to another, you know, along the chart, then it should kind of work out that it's a sometimes, but it's really got to be a direct path. Right? So I can't get to from rhombus to rectangle without passing through some other figure. Right? So if I could transform that rhombus into a square by straightening it out, then I would get myself to rectangle, but I I don't have a way of getting there in one shot. All right. But then you get into the missing angles. If you know the properties, and again, it's tall order, I just went over those properties for the first time, but opposite sides are congruent in a parallelogram. Opposite angles are congruent. That's true. Diagonals bisect each other. That's true. Right. So parallel side, like all that's wonderful, but a discussion of angles needs to come into play. In a parallelogram, opposite angles are congruent. Right. So anything that follows from the, again, I get stuck on the whole family tree reference. The ancestor that is parallelogram. Anything that follows beyond that would also have the properties of a parallelogram. Right. So whether it's a rhombus or a rectangle or a square, they're all going to have characteristic in that opposite angle that can grow to it. Right. So 65. Oops. That's wonderful. Useful information. Other pieces of information that are useful, all on the table above, is that consecutive angles are supplementary, but that's probably the trickiest one to remember. If you think about, and this goes way back to like the first class, in a quadrilateral, there are 365 total degrees. All angles add to 360. I think I said 365. 360 degrees. And copy, delete. So opposite angles are congruent. All angles add to 360. So the total of all four of the angles is going to be 360 degrees. And you can test that out in a simple case, like the case of a square. Each one of these is 90 degrees. So 90 times 4 is going to give you 360. I like a different way of thinking about it. In terms of quadrilaterals, I mean, triangles, we know 180 degrees, quadrilaterals, 360 degrees. When you get beyond that, like pentagons and hexagons, things like that, it gets more complicated. But I like the relationship that if you draw any kind of figure, whatever it is, number of sides, in this case, let's say just the 4, start off at one vertex and draw line segments to every other vertex. Here, here, and here. You just ask yourself how many triangles that you would have. All right, so I have 180 degrees here for this triangle, 180 degrees here for that triangle. Because I have 2 triangles, put it together, I have 360 total degrees. And it works. I mean, it just is a little bit of review, but it works for, let's say, a pentagon. I can draw a pentagon, which I really can't. Kind of. All right, so it's not a regular pentagon, but start off at one vertex, doesn't matter which one, draw line segments to each other vertex. Count the number of triangles. Each triangle accounts for 180 degrees. That would be 180 times 3, which would be 540 degrees. Right. So it's a nice little shortcut for getting you the total number of degrees within any kind of figure. Right. But again, we're only talking about quadrilaterals here, so any discussion of pentagons, 5-sided figures, hexagons, and so on would be beyond the purview of this lesson. But it's part of the conversation. Right. So if I know that there are 360 degrees in this figure, I could do 360 minus the 265s that I have. So 360 minus 130 is going to be 230. That 230 has to get split evenly among the other 2 angles. So I would just do a quick 230 divided by 2, and that's going to be 115 degrees. So each one is 115 degrees. So pretty straightforward, well, procedurally anyway. Computationally, it all depends. The numbers can be a little funky sometimes, but like they're within the constraints of adding up to 360 degrees, so they can't be that bad. All right. So, that jumped on me. Sorry. So this is going to be 70. So we're taking the 360 minus 70 twice. You can subtract 140 in one shot if you want. That's going to give me 120 degrees split evenly among the two remaining angles, which is going to give me, sorry. That would be 220, right? And that'll give me 110 degrees. Now you'll notice that in each case, each pair of consecutive angles adds to 180 degrees. Right? So for number one and number two, and they're both quadrilaterals, so it should make sense. Right? Or sorry, parallelograms. So these two angles add to 180. These two angles add to 180. These two add to 180. And for fresh new color, these two add to 180. And that holds true in any case involving a parallelogram. The opposite sides will be congruent, but also the consecutive angles will add to 180 degrees. And so it's a good way to either check or just do the work flat out. Now, when you have a trapezoid, different story. Okay? It can be easier or just as easy, but it would have, in order to find the kind of information that we just found for the parallelograms, we'd have to know what kind of trapezoid it is. Right? In this case, it's an isosceles trapezoid because two sides are congruent in length. Right? So isosceles trapezoid. Because the non-parallel sides are congruent. Right? So that would be these two sides, this one and this one. So in a trapezoid, especially an isosceles trapezoid, remember I was saying it's an isosceles triangle with its head chopped off. It's kind of grotesque even when you're thinking about geometric figures, but one thing that we know about isosceles triangles is that the base angles are congruent to one another. Right? So this would also have to be 49 degrees. Right? So then you get into some other things that we've talked about. Parallel lines and transversals. Right? So if I draw a line segment here, we know it's going to be parallel to this line segment. I'll just focus on one of these transversals, or otherwise known as a leg of an isosceles trapezoid. So let's say this one, for example. There were a lot of different sentences, conditional sentences that we use to discuss this, but we could say two parallel lines are cut by a transversal, then the alternate interior angles are congruent. We could say the alternate exterior angles are congruent. We could say if two parallel lines are cut by a transversal, then the consecutive angles are supplementary. All fun stuff. But then we could also say the simpler explanation, if we're not doing a proof, keep it simple. If two parallel lines are cut by a transversal, which is what we have here, the angles that look like they're the same size are the same size. The ones that don't add to 180. Those are the supplementaries. All right, so this would be 49 degrees. This would be 49 degrees. This would be 49 degrees. All right, none of those are helpful. You're like, okay, so that was a waste of time. All right, but if two angles come together to form a straight line, like these two do, then they have to add to 180 degrees. So that would mean that this angle right here would have to be 180 minus 49. So that would be 131. Right, so 131 degrees. Making this one also 131 degrees by the same reasoning, because we'd also have another set of parallel lines cut by transversals in which the given angle is 49. So there's no reason to think that this would be anything different, right? So what's going to happen again is you're going to have two angles that are the same and two other angles that are the same, and all four of them are going to add to 180. So a shorter way of doing it would be to say, all right, well, they're going to add to 360. You take your 360, subtract from it the 49 twice. Okay, so that's the same as subtracting 100 and then adding 2. So 262. And then dividing that by 2. And you get your 131 degrees there, right? Knowing that it's got to happen twice because those two angles are congruent gets you the remaining two angles, right? Number 4 is a case where we're asked to confirm that the following figure is a parallel. Oh, there's a typo for somebody. Right. So a measuring device to confirm that the following figure is a trapezoid. All right. So you need a ruler. So let me get my ruler out, which means I got to find my ruler. So let me pause 10 seconds for station identification. New York Mets. So we want, through measurement, we want to confirm that it's a trapezoid. But the length of the sides doesn't really factor into whether it's a trapezoid. It's whether it's parallel to, the two sides are parallel to one another. So you have to ask yourself, well, how can I demonstrate that two sides are parallel to one another? One way to do it is to measure the distance between those two sides that are supposedly parallel to one another. So if I take a point, let's say here, and then another point like over here, and then measure the distance from that point to its counterpart on the opposite side, that distance should remain the same throughout the figure. All right, so copy that. I'm going to use our ruler again for the next problem. So I'm going to measure this distance. And, again, it's kind of like wishy-washy because I could change my size on the ruler and I can make it whatever I want. But let's say I set it to this size. Then I'm looking at, it's a little blurry, but it looks like 1, 2, 3 more tick marks. So this looks like 4.8. So if I go this distance, oh, I wanted to be over a little bit. That's going to be about 4.8 centimeters. Now, if you're using a physical ruler, we talked about this earlier in the course, it's going to look different, right? Maybe it's 2 centimeters, maybe it's 10, like it all depends, right? So then what I want to do is I want to make that same measurement over here in this neighborhood. So I'll take my ruler without adjusting its size and just kind of slide it over and get this distance, which also appears to be 4.8 centimeters. Now, we're not asked to prove anything because in theory, if I'm going to make a proof out of this, I'd have to demonstrate that every one of these lengths from here all the way over to here would all be congruent, right? All those distances would be the same. And that, I mean, that's true. I can do that for many of them. I can't do it for all of them. You know, like there's infinitely many points between B and C. You know, so to be able to account for every single one of them is not practical / possible. All right. So that wouldn't work given the problem. Okay. So then I'll just move it off on the side for a little bit. So we've confirmed, you know, it's confirmed that the following figure is a trapezoid because BC is parallel to AD because the distance between BC and AD does not change. The distance between those 2 points does, or those two, well, yeah, between the points B and C, but the line segments BC and AD does not change for all relevant points. You know, because there's some points over here that don't matter. Like in this neck of the woods, we don't care about it because BC is already ended. Right. Now, to confirm that a figure is a rectangle, different conversation. I can show that the distances from here to here are going to be the same as the distances from here to here and so on across the board. But all I would have succeeded in showing is that those two sides are parallel to one another. And then if I did the same thing going from here to here, I would have succeeded in showing that these two sides are parallel to one another, which doesn't demonstrate that it's a rectangle. It demonstrates that it's a parallelogram. All right. So we want the quickest, easiest way to demonstrate that the figure is a rectangle. Well, in order to be a rectangle, at first it has to be a parallelogram. All right. So parallelogram. Now, if the diagonals are congruent, that parallelogram is a rectangle. So a parallelogram with diagonals congruent. All right. Now, earlier I mentioned that one of the characteristics of a parallelogram is that the diagonals bisect each other. All right. So we could demonstrate that a figure is a parallelogram if the diagonals bisect each other. So instead of showing that all of these distances are the same and all of the distances going the other way are the same, what I can do is show diagonals bisect each other. All right, that would demonstrate that it's a parallelogram. All right, and then once I've done that, now I know it's a parallelogram. All I'd have to do is show that the diagonals themselves are congruent. I could even start with the part where they're congruent. All right, so I'll take my ruler and get a little length here. You know what? It really doesn't matter. Get my ruler on there. All right, the way I have it set up, it's about 12.5 centimeters. All right, so then I need it to go the other way. And that, you know, we've kind of run into this issue before. I need it to not change its size. So You're just going to kind of have to believe me, because it's going to change its size. But if I were to take my ruler and rotate it up, I should get 12.5 also. Okay, so it's about the same to the maintaining its size. I have two rulers. Let me put the other one back in, that show a length of 12.5 centimeters. So each diagonal, and you know what? Let me get some labels on this. Move this out. I'm going to call this A, B, C, D. DB, the measure of DB, is the same as the measure of AC, specifically 12.5 centimeters. So therefore, 3 dots in the form of a triangle means therefore it's a parallelogram. Right, so we have that covered. So then what I want to do is show that they're bisecting each other. All right, so going from A to, let's call that point E in the middle. And we can get rid of those numbers. They're not really helping. Honestly, I don't remember why I had them. Probably copied and pasted from another figure. I'll take it as a typo. I mean, any change that I make, obviously I'll take it as a typo. Keep forgetting to change it. So going from A to E should be the same as E to C. All right, so let's verify. Going from A to E, we're looking at, it's just a question of, could we call that 6 1/4? Well, we're not going to call that much of anything yet, but yeah, that looks like it could be 6 1/4. I mean, again, it's a rough estimate based off the precision of the ruler, but each one of these looks like it could be 6.25. Okay, so we just want to see if it's going to work that way the other way. It looks like it's roughly the same length in both cases. Right, so we have enough evidence to really demonstrate, we're not proving anything, like I said before, that each one of these line segments here is 6 1/4 centimeters. Okay, so we would say, let me just darken that. The measure of A to E is equal to the measure of E to C, which in turn is equal to the other two, B to E, E to D, and they're all equal to about 6.25 centimeters. So therefore, it's a rectangle. Right? And that's because if all 4 of those sides are congruent to one another, then each piece must be half of the whole. Right? If they're half of the whole, then it must be that they were bisected. So AC was the knife that cut DB in half. And also simultaneously, BD was the knife that cut AC into 2 congruent pieces. Right? So I know, like with the digital ruler, it's never pretty, but, or at least the process, just all I can do at this point. You know, it is what it is. Let's do confirm as the first word of the day. Confirm. All right, so once again, confirm is the first word of the day. And then we'll do one more example and then we'll take a little break. So just to confirm, we're going to do one more. I know, cheat ball. Just saw the Sonic movie today. The second one, obviously the second one. a lot of cheesy humor in it, so it was right up my alley. Yeah, just my personal way of being. The cornier, the better. I could tell my wife really loves that about me. So anyway, number 6 in the diagram below of rhombus ABCD, angle C is 100 degrees. What's DBC? We can figure out everything, but they just want DBC. They just want this jammy right here. So properties of quadrilaterals, it all comes into play. So in a parallelogram, and again, the hierarchy, I'll just get my little hierarchy diagram back here. We have the parallelogram begets the rhombi and the rectangles, which in turn beget the also biblical, the square. Right? So the first characteristic that we want to keep in mind of something that would be a rhombus would be that it's a parallelogram. So opposite sides are congruent, opposite angles are congruent, right? Opposite angles are congruent. So that would mean that this is 100. Right? Consecutive angles are supplementary, but even if you don't like that, you could say, all right, well, I know that there's 360 degrees in the figure. I'm going to knock off 100 degrees twice. That gets me to 160. If these opposite angles, the whole shebangs here, are congruent, they have equal measure. So they have to be the same, but they also have to add to the remaining degree measure that's available, which is 160 degrees. So divide by 2. That gets me 80 degrees. So the whole thing is 80 degrees in each case. Right? So then it begs the question of, all right, well, what about that little piece? What about that little sliver that we care about there? Well, there's 2 ways to handle it. One, another property. Okay? In a parallelogram, and we haven't really talked about this, but in a parallelogram, the diagonals bisect the given angles, which is useful. Right? But if you don't think about that, you have another option. So I could put aside my 80 degrees for a second here, because really we have our answer if we know that those angles are getting bisected and each one has to be 40 apiece. Right? But let's say we didn't recognize that. Or maybe you suspected it, but you wanted to confirm it. So we think back to triangles. So ignore the top triangle and just focus on the bottom. All right. So the second way of getting this would be to say, all right, this is a triangle. These 2 sides are congruent to one another, this side and this side. 2 sides congruent in a triangle makes that triangle into an isosceles triangle. So in an isosceles triangle, 2 angles are congruent to one another. Well, it can't be the case that one of the other angles is 100 degrees because that would be more than 180 that you have available. So it must be that these 2 angles are congruent to one another. If they're congruent to one another, then they must be 40 apiece. So you can get your 80 and split it in half like we were doing before. A little busy diagram now. But you could get your 80, split it in half like we did before, or you could use isosceles triangle knowledge to get you there. Either way, you're coming up with the measure of angle DBC is equal to 40 degrees. Okay, so it's a little kooky, but definitely manageable. But it requires you to, kind of process all the information, like based off of, right? Yeah. So there's numbers that are given to you, but all these properties that come into play. So if you know all the properties, that's great. Then there's nothing else to teach you. Because if you looked at that table with all the properties and said, "Oh, this is so easy, I know it all already," then there's really nothing else going on here, right? But if you know some of them, you might not know the right ones, or correction, the intended ones. So I might look at this and say, all right, you're going to use your knowledge of quadrilaterals, but you say, well, I know this about triangles, so I can figure out what I need to figure out that way. The same is going to come through in the remaining examples. But like I said, let's take a 5-minute break at this point. So I got 3 different clocks at say 3 different times. So this clock says 7:23, so we'll say 7:28 by. Well, not that it matters. 5 minutes from now. All right. So let me pause the video. 0, 0 second. So number 7 in the diagram below, LATE. Not the best situation. Yeah. Pretty apropos. Yeah, trapezoid, LE congruent to AT. Right. So LE, a little tiny segment on the fringe there is congruent to AT. So if we know that they're congruent, then they're both going to be measured at 10 units. LA is 24, that was marked on there already. ET is 40, AT is 10, or they already mentioned, well, we already addressed that. Altitudes, LF and AG are shown. Now, if you didn't know what an altitude was or you forgot, or some mixture of the two things, that's okay. They mark in the little right angles there for you, so we got a little help, right? Now, opposite sides of a trapezoid are parallel to one another, not congruent. As you can see here, we got 24, we got 40. Those are certainly not congruent, but opposite sides of a rectangle are congruent. So if we take a little closer look here, you would see, and just kind of highlight the part that I'm referring to. This piece here appears to be a rectangle, right? So what we would want to do is, well, we don't have to prove it on paper, but we want to think about the characteristics of a rectangle and see if that holds, right? First off would be opposite sides are parallel, right? Well, that's fine. It's LATE is an isosceles trapezoid, right? Forget about isosceles, it's trapezoid, which means these two sides are parallel to one another, right? The verticals also would be parallel, and this goes way back. If two lines are perpendicular to a parallel line, they're parallel to one another. It was in the same conversation that we had when we talked about parallel lines and transversals. It was just the one that we never really used, right? So it's kind of like, what is it? The enemy of my enemy is my friend. No, it's the same idea there, where you're saying, all right, you're perpendicular to this line. You're also perpendicular to this line. Well, then you must be parallel to one another, all right? So your interests are in alignment. So these two would be parallel to one another, which doesn't make it a rectangle. It makes it a parallelogram, right? Now, that's actually good enough because in a parallelogram, opposite sides are congruent. Yeah, opposite sides are parallel, but opposite sides are congruent also, right? So that's enough for me to say that this line segment here, squiggly bracket game is all out of whack. There we go. That's going to be 24 units, right? So if we know that that piece is 24, then we know that we're going to have 16 left over for these two sides here, right? They want the length of LF. They want this piece here. I need some kind of justification to say that these two line segments are congruent. They certainly look like they are, but I want to be able to say certainly that they are. And so, there's a couple of ways to handle that. One would be, again, parallel line relationships and all that good stuff, right? But also you can get into, well, it's an isosceles trapezoid. which means it's an isosceles triangle with its head chopped off. So I'm going to draw that morbid figure down. All right. So if I know that the whole thing is an isosceles triangle, then I know that the base angles are congruent to one another. All right. So I know that this piece is congruent to this piece. All right. Now, this is another important characteristic here because it's not something that comes up very frequently. When we talk about triangle congruence, we didn't really address this one very often. In fact, I think it was just in the opening example, and that was the end of it. But if I know that, and I'm just going to remove these markings here for a second. These two sides are parallel to one another. Then I know that these two distances have to be the same. This distance has to be the same as this distance. All right. Now, it doesn't seem like much, right? But we know that this angle here is 90 degrees. We know that this angle here is 90 degrees. All of these angles are 90 degrees. That's wonderful. All right. I mean, you got options because I can go angle, side. I can go hypotenuse, leg. But bottom line is I could demonstrate that these two triangles are congruent to one another. Right? And that's going to be helpful. Right? Because let's just get this out of here for now. And say that the only thing we know, and we're just going to fix this a little bit, is that these relationships are true. That these two sides are congruent to one another. Right? If we know it's a right triangle, and these two angles are congruent to one another, then these other angles must also be congruent to one another. Since I know that this side is congruent to this one, this line segment is congruent to this line segment. So those two sides are congruent also. And I know that the included angle is congruent. I can say triangle EFL is congruent to triangle TGA by, I can go SAS, right? The side, the angle, and the other side. I can go angle, side. Right, that would be this angle, and this side here that's not in between those two angles. I could say angle, side, angle. So angle, and the included side. Or the one that I was alluding to before, the hypotenuse and the leg of a right triangle. If the hypotenuse and corresponding hypotenuses and corresponding legs of two right triangles are congruent, then those two triangles have to be congruent. So the HL theorem. All right. So then, all right, we got that piece of information down. Bringing back my parallel. Just for the notation there, I can now say that EF would be congruent to TG by CPCTC. All right, so you're kind of looking at it like, well, we kind of already knew that because they looked like they were congruent, but just because they look congruent doesn't mean that they are, right? So we were able to, it wasn't a rigorous proof in the sense that we didn't make the statements, the reasons, and justify each one of these, by putting down our full thought process. But the explanation, you know, the hand waving that I just did, is really what gets that idea across. All right. So if I now know that these two line segments are congruent, this one and this one, and we already have 24 units accounted for out of the 40, then there's 16 left over, they have to be 8 and 8. All right. So if I want LF, I could just use the Pythagorean theorem. A squared plus B squared is equal to C squared. 8 squared plus some unknown vertical side, B squared, is equal to 10 squared. Assuming you don't remember your Pythagorean triples, 64 plus B squared is 100. B squared is equal to 36. And B would be equal to, because we only care about the positive square root, B would be equal to 6 in the Pythagorean theorem. So that tells me, therefore, 3 dots in the form of a triangle means therefore that LF, or the measure of LF, is equal to 6. All right. Now you wouldn't have to, you know, for a question like this, the way it's structured, you wouldn't have to show all these little details along the way, but that, you know, instead of just looking at it and say, well, I think they're congruent because they look like they're congruent, you have some kind of justification going on there. Right? Just knowing the relationships that exist. And the markings are really what gets it done. Right? So, you know, when you're not making a proof, the markings, you know, like I said, the rigorous proof and the statements, the reasons and all that, the markings are really, they're really the shorthand way of representing a proof. Just marking up a diagram is showing that you're aware of the relationships. Like in number 8, use the rhombus and the given information to find each measure. Yeah, we got numbers and stuff. But what do we know about rhombus? Rhombi. All sides are congruent. Opposite sides are parallel to one another. Just like a parallelogram. Because it is a parallelogram, right? The diagonals bisect each other. All right? The diagonals intersect to form right angles. Put a little square there to show that each one of those angles is a right angle. All right? So there's a lot going on there, but basically this is like I was saying, a shorthand proof. So did I justify each one with a rule? No. But just by virtue of placing the markings there, it's basically showing that I know all this stuff. But then another one, the diagonals bisect the given angles. So bringing it on in, this angle here is going to be congruent to this angle here. Right? And if opposite angles in a parallelogram, rhombus is a type of parallelogram, if the opposite angles are congruent, then each one of these would have to be the same. So each one of these is 59 degrees. Right? I don't know the length of this side, but since this side is 12 centimeters, this side has to be 12 centimeters. Right? So this segment and this segment have to be the same. Right? Now, if we know, let me just bring it back here, that there are 360 degrees in a quadrilateral, I can knock off the 59 4 times. Right? So subtracting off 59, 59, you don't have to write it out 4 times, you just do the computation of the show anywhere, you know, just for the notes. All right, so 60 times 4 is 240, knock off 4, so 236. Well, actually, let me subtract, so 120, 124. just double check that. So yeah, so 60 times 4 is 240. 360 minus 240 is 120, but I didn't want to subtract off 60. I wanted to subtract off one less than 60 4 times. So add on 4. I think it's 124. All right, now these two opposite angles, this one and this one, are going to be congruent. But again, if they're going to get bisected, that means that these two angles have to be the same. Now, you don't actually need quadrilateral properties to figure that out, because if you know that this one here is 59, and this goes back to 2 examples ago, where you could use your knowledge of triangles to get the job done, or you could use your knowledge of quadrilaterals and get the same, accomplish the same objective. But if you're looking at just this triangle here, just this guy over here, we have 90 degrees already accounted for right here. 90 plus 59 is 149. Subtracted from 180 is going to be 31. Right, so that would make each one of these 31 degrees. 31, 31. Since we know they're all congruent, they're all 31. Or I could have just taken this and divided it by 4. And that would have given me 31 degrees. Either way, we got what we were looking for. Now, I am going to pull out just a single triangle, because we know everything there is to know about this rhombus, except for these 2 vertical line segments here. Right? Because I know the rhombus has all 4 sides congruent. So if this one is 14, then this has to be 14, 14, and 14. If I can just look at one of these triangles, I'll just take this one right here. Kind of pull it out, take a look at it. It's a right triangle in which a leg is 12 and the hypotenuse is 14. I can figure out the missing side, call it B. So A squared plus B squared equals C squared. 12 squared plus B squared is equal to 14 squared. 144 plus B squared is equal to, is that 196? I think it is. I always struggle with my 14 squares for some reason. Yeah. So then I'm going to knock off 144, and we're going to get 52. Right, now that's not a perfect square. So when I go to take the square root, I need to break that up into factors that are perfect and not perfect. So B, square root of B squared is just B, but that rad 52, I have to break that up. All right. So you know, it might not be the case that you end up with perfect squares. You know, it's not always, I mean, it would be ideal if it were the case, but it's not always the case. Factors of 52, 4 and 13. 4 is perfect, so we're looking at 2 rad 13. All right, let me just do a quick double check on that. I'll pop it into Desmos. All right, so I would need 12 squared plus 2 rad 13 squared. Oops. Do it again without the oops. That's 196, which is what 14 squared is. All right, so that means that the B side here is 2 rad 13. It's a nice exact value. Not pretty, but It's better than the decimal equivalent, so we'll take it. You know, but that's going to be the length of this vertical side here, which corresponds to, you get a different fresh new color here. This vertical here is 2 radical 13. All right. So now we did all that. Probably, I mean, I got to imagine overkill. But we did all that. Now I suppose it's probably a good idea to answer the question that was being asked. So BCE, right? BCE is this one over here, right? And you got to be careful because, like, if I were to say angle C, for example, I could be talking about more than one angle. But BCE is very specific. It's starting at B, going to C, ending at E. So it's got to be this angle here, which is 31 degrees. Right, BEC, that's the route that we're taking. So starting with B, going to E, ending at C, the angle that's formed would be that right angle. So that's 90 degrees. Little typo notation issue here. This should be the measure of side C. I'm sorry, AC. I could not get a straight line segment to save my life here. Ugh, I had it too, and it just moved on me. And the same thing with E. E should be the measure of AD. Little notation thing. So AC, that's the whole line segment going from here to here. Right? 12 and 12 gives you 24. So 24 units, but we'll just say 24. ABD, so starting with A, going to B, down to D. I know the diagram got a little crazy here, but that's talking about this angle up here, which would be the 59-degree angle. And then AD, well, AD is just this hypotenuse, which is 14. Okay, so you're like, oh, what's the deal with all that radical business? They didn't even ask for that. Well, they didn't this time, you know, but we went over radicals for a reason. So we want to be prepared for it. And also, first time we're doing an example like this, it makes sense to figure out all the bits and pieces. Okay. When we get around to it, I'll talk to you about the area of this rhombus. I kind of feel like talking about that area right now. Yeah, why not? So just off on the side here, area of rhombus ABCD. We haven't talked about area as it applies to quadrilaterals yet. But then when you think about it, what are quadrilaterals except multiple triangles pieced together? So if I could figure out the area of a triangle, area of a triangle is 1/2 the base times the height, or base times height divided by 2. You know, either way you want to think about it, we can kind of get this pretty easily, right? Because if you look at each one of the triangles that makes up this trapezoid, now you got to be careful. Again, this diagram, it just got kind of way too crazy. Let me just do a quick cut. I'll put it all back in a minute, but let's just focus on the fact that we have 4 congruent triangles here, right? Because this one here has a measure of 2 radical 13, 2 radical 13 by 12, right? This one, so that's this triangle. This one, also a length of 2 radical 13 by 12, same triangle, right? This distance here is 12, so we're looking at 2 radical 13 by 12, and another 2 radical 13 by 12, all with hypotenuse is equal to 14. They're 4 congruent triangles. as promised, this disgusting diagram back for your viewing pleasure. All right, so this is 4 congruent triangles. Going crazy with the abbreviations, right? So if I could figure out area of one of those triangles and multiply it by 4, then we're good to go. Right? So alternatively, what we could do is do that all in one shot. So 4 area of triangles would be 4 times 1/2 the base times the height. Right? So the 4 area of a triangle would be area of a rhombus. Romulus. That's going to be equal to 2 times the base times the height, right? Because that's the 4 times the 1/2. Now, the purpose of me showing this to you is not to torture you. Well, that's number 1. And number 2, it's not to give you another formula to remember. It's more so that you can look at it and say, oh, here's a formula that I don't really need to know, because all I need to know is the area of a triangle. I could just figure this out, right? So you'd have to think about what the base and the height is. Well, the base, this was a base. And, let me just generally draw a triangle. I cannot draw a triangle. I have base times height. Here's the base, here's the height. All right. So the base and the height make up the half measures of the diagonal. Right? So this right here, I can show you, this base value, use a highlighter. That's half of one diagonal. And this other value, the height, is half of the other diagonal. So we have half the measure of a diagonal multiplied by half the measure of another diagonal. So 2 times a half times a half. Well, 2 times a half is 1. Right? Times another half would be 1/2. Half of one diagonal multiplied by the other. So diagonal 1 times diagonal 2. And that would give you the area of a rhombus. Now that, again, that's a rule, but you don't really need to know that rule, because if you find the area of the triangle, 1/2 of 12 times 2 radical 13, you get 6 times 2 radical 13, which is 12 radical 13. That's not a 13. If I want to find the area of the rhombus, I would take that 12 radical 13 and multiply it by 4. And I would get 48 radical 13. Right? Alternatively, I could find the product of the 2 diagonals. So just kind of going back to this newfangled formula that was invented by a person who wishes to remain nameless. No, I didn't invent it. Reinvented more than anything else. The first diagonal, the whole diagonal is 24. The other diagonal would be twice this, which would be 4 radical 13. And when you carry out the multiplication, 1/2 times 24 is 12, times 4 is 48. You get 48 radical 13. So it's kind of nice in that regard, in the sense that you can create a new formula. I mean, that's more of the mathematician mentality of like, let's create a formula that works out every single time. And then you have the more practical sense of like, let's just get the answer to the question, right? And it's like, well, what's the question being asked? It's what's the area of a rhombus? But then it's like, well, what if we were asked to find the area of a rectangle? What if we were asked to find the area of, you know, whatever it happens to be, a trapezoid? Things like that. It's a matter of just recognizing what are the parts that make up the figure and going from there. So actually, instead of getting into the proofs, let me, yeah, I'm going to put that on the burner for a week. Oops. And I'm going to throw in another page here with just a couple of examples here of area problems. So we'll say, what do they call this? Question. Oh, okay. So I reset the clock after this. So let me do 9. This will be find the area because this will tie in nicely when we get into the 3-dimensional stuff, but more on that later. Not later today, but later. So find the area of the rectangle. I'll say quadrilateral. And let's make it a rectangle ABCD. When I give the name of the figure, it gives me license to draw like the world's worst diagram by hand. Because, well, I should probably hang on to that for the trapezoid example. Example being the second word of the day. Okay, let's say that this side is 3, and the hypotenuse, well, I'm giving it away here. The diagonal is 5. Okay, then we'll say trapezoid, isosceles trapezoid. I'm just going to draw, I'm going to use my strategy of drawing a isosceles triangle and chopping its head off. And even that's not perfect. Again, ABCD. And then we already did the rhombus. It wasn't pretty, but we did it. But we'll say parallelogram, ABCD. With base of 20 and line segment here being 8. All right, so 3 fresh new examples. Every one of them a typo. You know, not now, they're fine, but they all should have been included in the lesson. So that makes it a typo. At a moment of panic's not the right word, but it was not comfortable a second ago with the thought that I might not have been recording this entire time, but I am. But doesn't stop my heart from skipping a beat. I tried to make it better, and I think it made it. So in the first, I didn't label up the Isosceles Trapezoid. That one should be pretty easy to do because we've already kind of addressed the nuts and bolts of the Isosceles Trapezoid. But let's say A to B here is 14 and D to C is 6. I'm trying to keep the numbers reasonable, but not perfect. All right. So let's, again, start with the rectangle and go from there. And then this will be the last thing we do for tonight, I think. Yeah, we're kind of at that point. So if we were given the base and the height here, it would be great. For the rectangle, not the case. Right? They gave us the height and something other than the base, which you know, it's information. You know, so we just kind of live with it. But we could figure out the missing side because we know information about right triangles. Now, as long as we know that all angles in a rectangle are right angles, then we're in good shape here and we can figure out what we need to figure out. All right. Now, these two triangles, now you could figure this out without going down the triangle road here, as it were. But let's say we're focusing on just the triangle aspect. We have two congruent triangles, which means that ADC with a bar? No, triangle ADC is congruent to, it really doesn't matter what we call it as long as the B is in the middle. I'll say CBA. Right. So those are congruent, which means that if I wanted to find the area of a rectangle, I would just need to find two times the area of the congruent triangles. An area of a triangle is half the base times the height. All right. So the substitution here is area of a triangle, half the base times the height. Multiplied by 2 gives me the area of a rectangle. 2 times 1/2 is 1, giving just a BH as a result. All right. So it's not a proof, but it is a justification in the sense that we now have, you know, it might be like a prequel kind of deal when you're watching a movie and then they put out a prequel, like, you know, the Star Wars prequels or something like that. And you're like, oh, you've answered the question that I never really had interest in. You know, it's like, why did Han Solo care about the dice? Well, they were a good luck charm. That's about it. You know, but then, you know, things like that. All right. So here we now know that area of a triangle is base times height. And you're like, okay, thanks, Doofus. We knew that for like the last 20, 30, 40 years, some of it. But we now have a justification. And a lot of this course is based off justification. Right? So I need this missing side here, which I'll call A. Right? It's Pythagorean, so A squared plus B squared is equal to C squared. A squared plus 3 squared is equal to 5 squared. A squared plus 9 is equal to 25, which means A squared is equal to 16, and A is equal to 4. All right, so now we have the base, because opposite sides in a rectangle are congruent. The base is 4, the height is 3, so the area of the rectangle would be 4 times 3, which would be 12. And again, like I said, it's ask and answer. You know, like, okay, well, Could figure that out without taking this class. Yeah, I know. But sometimes you want to know how Han Solo got that blaster. And this is one of those moments. Right, so the isosceles trapezoid. I'll leave that all up on the screen for a second. We talked about this before. We know that if we drop altitudes and split the base by the altitudes, the opposite sides are congruent, which means that this little segment here has to be worth 6 units. We also discovered or reviewed that these two segments are going to be congruent in length. Right? So now remember, the whole point is to find the area. So I know that these two line segments here have to combine to give me 8 units. So each one has to be 4. All right, now I do have to, I just realized I do have to give you another piece of information. You got to know either the hypotenuse or the height. It's more interesting if I tell you the hypotenuse rather than the height. So let's say the hypotenuse has a value of, I'm going to go with, no, I used 5 already, 6. So I'm going to make it so that this length and this leg are equivalent to that. Right, so I'd use the Pythagorean theorem to find the missing side here, because area of a triangle, again, half the base times the height. I have 2 congruent triangles and a rectangle. And we just discovered that the area of a rectangle is base times height. Right? So if I take 2 of those triangles, 2 areas of the triangle, we already know that that's going to give us a base times the height. Right? So it's just a different base and a different height. I can figure out the area of the combined figures on the outside, right? Which is wonderful. Or I could do it independently and work on it, just add them together after. But bottom line is, I'm going to need to know what this vertical line segment here is. So I'll call that B. We'll just do it off on the side here. 4 squared plus B squared is equal to 6 squared. 24 plus B squared is equal to 36. B squared is equal to 12. And when I take the square root of both sides, that 12 can be broken up into a rad 4, rad 3. So that's going to be 2 rad 3 for each one of these verticals. All right, so I could figure out the area of the rectangle immediately. I could also figure out the area of the triangle. Now, it's kind of interesting. If I look at this as 1/2 the base times the height, I can look at this as in 2 possible ways. Let me just show you. Let me get rid of this for a second. I'm going to show you what would happen if I took this triangle out and coupled it. That's not what I wanted to do. All right, let me try that again. I'm just going to overshoot it a little bit. So I'd only grab the part that I need. Oh, okay, I thought that would have worked. There we go. Okay, so I got one triangle here. Now if I take the other triangle, which is basically a congruent triangle, but on the other side, I just really got to get in there to grab it. There we go. put them together, I get one triangle, right? So that would be this piece here. Okay, that looks terrible. And this piece here. All right, putting them together creates one triangle with a total base length of 8 and a height of 2 radical 3. So when I want to find the area of this triangle, I could use the area of a triangle formula, but on the combined two pieces rather than independently. Right? So I would say 1/2 of 8 times 2 radical 3 is going to be, well, 8 radical 3. And then the base times the height, I got a base here of 6, a height of 2 radical 3. Base of 6, height of 2 radical 3 is going to give me 12 radical 3. I could just add them together. Right? So the area of the trapezoid would be 12 radical 3 plus 8 radical 3, which will give you 20 radical 3. So you can do it that way. Another way to handle it would be to kind of account for the fact that you have multiple bases, one for the two triangles on the fringe and one for the rectangle, right? So there's ways of handling it that way. There's a nice shortcut formula for isosceles trapezoid, but it involves a little bit more work than developing this rule here. So I'm just going to give it to you. The area of a trapezoid formula is 1/2 the height times base 1 plus base 2. And those two bases are interchangeable. Right? So if you carry it out using this formula, you'll get the same result, 1/2 times 2 radical 3 times 6 plus 14. That's going to give you 20 radical 14. 20 radical 3. All right, so you can do it that way also. All right, but that, again, it's another formula, it's another rule. One way involves you understanding very basic geometry. And that's not to sound condescending or anything. It's just like, what's more basic than squares, rectangles, and triangles? So very basic geometry or more formulas. Right? So that's kind of the idea there. Now, if you did do it using the more elaborate approach, I guess you'd have to. So to come up with this formula, you'd have to involve subscripts in the area of a triangle, area of a rectangle, stuff that we did before. So it gets a little much. So that's one of the reasons why I just kind of mixed that. But the last one is the parallelogram, and that is probably, I think, let's say one of the simpler cases, because if you visualize what a parallelogram is, I'm going to drop an altitude here. I'm going to drop an altitude here. I'm going to create a rectangle in the middle. And it's like, okay, well, it seems to be very similar to what we just had, like in terms of the trapezoid. But if I take, and you might have seen this before, it's kind of a clever way of looking at a parallelogram. You take this piece here and move it over to the other side, physically lift it up. Let me just grab this back. Take this piece and just bring it on over here. Not quite. Yeah, I wish. Well, one day I'll learn how to draw, but you get the idea. You take that piece and move it over, you create another rectangle, or just a rectangle. Because this new piece that we created would be another rectangle, but the whole thing, again, if I'm transporting one piece, this piece here is gone, it's getting moved over here. Now I'm looking at a geometric figure that is a rectangle. And if I could figure out the area of that rectangle, then I'll have the area of the parallelogram. It turns out that the area of the parallelogram is the area of the rectangle. It's the same deal, right? But I wanted to show you a different way of handling it, right? So we know that opposite sides of a parallelogram are congruent. Right, so that side is 8. I'm just gonna make this a little smaller. This side is 8. Right. So I would need to know the area of each of these two triangles and the area of the central square. Right. And it doesn't seem like I have much information at all to be able to handle that, but we actually have plenty of information. Right. We know we have right angles. So I got one here, and I got one here. Okay. Just real quick. Right. And again, we know that the whole base here, this whole segment, is worth 20. Now we can go after this using an algebraic approach. It's not always the most entertaining thing to do, but let me just show you. I'll give you the gist of it, because we already know how we're going to figure out the area. Just a matter of doing it. But if I tell you that this length here, is, we'll call that x. Then this length here has to be 20 minus x. And so I try to keep the algebra light in this class, but sometimes it's kind of necessary. All right. So if I take this piece here and move it over to this side here, then I'm going to get another little segment here that we're just going to call, it's the same length, so I would call that x. Right. So then if I wanted to find the sum going from here to here, it's still going to be 20 minus x plus x. And I'll just show you off on the side here, 20 minus x plus x. I mean, you don't have to be a whiz with algebra in order to see that these two things are opposites of one another. They're going to cancel out, and you're just going to be left with 20. So whether I take this piece here and call that 20, because x plus 20 minus x, or if I take this piece here, it doesn't make a difference because they're both the same. Right? So then what I would do is drop the altitude. And that gives me the figure that I'm looking to find the area. Right? So then it's just a matter of finding the area, because I know that the base, quote unquote, the base is now 20. I just need the height. So that would be either of these two segments, this one or this one. It wouldn't make a difference. All right. So these two, this one here and this little space here, are combined to give us the figure that we're really looking to try and find the area. Let's go down to 1. try to make it a little bit more obvious. All right. So I just need that height. So I could set up some algebraic equations, but that's going to make things more complicated. You know, like I said, I wanted to stay away from the algebra. It's really more about proving a point. So let's say, for example, I'll give you something specific here. Let's say, for example, x is 3. So instead of saying it's x, it's 3. All right. So now I know this little segment here is 3. I can figure out the height. All right. So I pull out the triangle. 3, 8 with a hypotenuse of 8, right triangle. A squared plus b squared equals b is equal to c squared. 3 squared plus b squared is equal to 8 squared. Nine plus b squared is equal to 64. B squared is equal to 55. That's not something you can break down, so b is going to be equal to root 55. All right. So that gives us this line segment here to measure anyway. That 55. Area of a parallelogram is the same as the area of a rectangle, which is base times height, which is 20 times the square root of 55, which would then be 20 radical 55. All right. So the variable stuff there was just to kind of make the demonstration have a placeholder. Really, it wasn't, I had no intention of solving this algebraically. So we'll just go with that. And besides, I don't even know if I gave enough information to solve that algebraically. But you can definitely do it with trigonometry, but that's a different course. All right. So yeah, for example, if x is equal to 3, this is how it would have played out. But the whole point behind the x is to show you that, oh yeah, that distance is x. What would happen? It would move over and it would become a rectangle. What's the area of a rectangle? Base times height. So therefore, the area of a parallelogram would be base times height. All right. So I know that was kind of a lot. It's kind of like a crash course on quadrilaterals all in one session, but it's kind of necessary to take some time to digest this, because when we talk about the proofs next class, it'll kind of go a long way. All right. So yeah. All right. So that's all I have for you this evening. So let me stop the recording.